before. I know a couple have. So what I'm looking at really is these sort of interactions of icy particles where the friction might be dominated by a thin film of liquid rather than solid contacts. So the kind of thing I'm thinking about is really, this is a photo here of Mount Rainier up in Washington State in the USA. And it's a huge volcano that's got a glacier sitting on top of it. Okay, so that doesn't seem like a really good idea. So we've got a geothermal heat flux, which is fairly constant, but we all know that there's a radiative heat flux from the sun, which seems to be increasing. And that's simultaneously decreasing the stability of these types of glaciers. So the USGS is starting to report increased incidences of ice falls from these types of locations. And here in the foreground, we've got the city of Tacoma, about 20 miles away. And in fact, it's well within the realms of possibility that a fairly large chunk of ice could fall off that glacier and through a process of secondary debris flow type events could easily reach Tacoma. Okay, so the second motivation is that Charles Harris and Michael Davis, they looked at rock faces that were held together by permafrost. So this is kind of an interesting problem, because if such a rock face collapses, it will be the cracks where it all breaks up. And so when you're talking about a granular flow of such a rock face collapse, the actual contacts are going to be ice contacts rather than rock contacts. So maybe we should be looking in a slightly different way at the types of friction laws that describe those. So as we've seen, volcanic ice caps can also trigger lahars and secondary debris flows. So an interesting case study which I wanted to show you, you probably come across this, was in Kolka-Karmaden in the north of Seashire, the northern flank of the Caucasus Mountains in 2002. So the top photos there are from NASA Earth Observatory, the satellite, and from top to bottom that image is about 15 kilometers long. Okay? And the right-hand image is before, and the left-hand image is afterwards. And here at the bottom we've got a panoramic view of the same river valley, which runs from bottom to top on the upper photo. So what happened was that essentially a rock face on this mountain at the back there collapsed on top of two glaciers and almost entirely entrained the two glaciers. It was then funneled down this valley and then got trapped here at the entrance to a gorge. And it left deposits of hundreds of meters of depth of glacier ice. So this was a really phenomenal event, 15 kilometers and reaching speeds estimated at up to 80 meters per second. Okay. So what's interesting about this event was firstly the extreme mobility. How did it travel so far and so fast? And also how did that debris flow, that ice-bearing debris flow, how did it eat up so much of the valley bottom and erode the material into it? Okay. So I was asking the question then, can wetting through the presence of the glacier ice in there, can that lead to different frictional laws, and also can it enhance the erosion in some way? Okay. So why I think this might be the case is that any crystalline substance, including water, the very, very top crystal layers, the outermost crystal layers, no longer preserve that crystalline structure. So there's some kind of disordered structure, and this is termed pre-melting. So it means that ice, even down to minus 20, minus 30 degrees Celsius, has a very, very fine film of water coating it. Okay, and that's why you can skate ultimately. Okay, because when you can't take ice skates on concrete because you don't have this type of film, but on ice it works because you have this very fine film of water. And secondly, when I was little, I always went down near the sea to build my sandcastles like this. Okay, because I knew that wet sand has very different mechanical properties that allow me to build it up compared with dry sand, which would just fall down. So I think pre-melting plus this big mechanical difference of wetted materials might lead to different dynamics. So the experiment I did was to take a rotating drum, very narrow, it's almost like a Healy Shaw type cell, and I filled it with ice particles that were around about 5 millimeter in diameter. So the thickness of this drum here is 4 particle diameters. I'm not actually interested in the granular flow inside the drum. All that I'm interested in is using the drum as a way to generate a continuous shear flow of ice particles that I can observe over a long period of time. So what this is doing for me is that it's creating that granular flow, and it's also reproducing some kind of bed friction, well, conveniently, essentially. And because it's a continuous flow, I can observe it over a long period of time and see the subtle changes due to the melting. The ice particles I made by dripping water very slowly into a bath of liquid nitrogen, and that literally freeze-dries them. And then I can store them in a freezer for a while, and I need to use them quite quickly because they do degrade over some time. But it makes, you can see up in the photo up there, it makes a bit of a uneven particle size distribution. But in fact, the experiment's kind of convenient because granular segregation, it means that it's always going to be the same particles going through the shear layer that I'm interested in. So although it's a non-ideal manufacturing technique, the experiment helps me out of it. Okay, so with the experiment, I've really got 2 aims. Firstly, asking myself, well, does this pre-melting, does this liquid film, does it affect a granular flow of ice? And secondly, do granular collisions actually enhance that pre-melting? So do I get additional wetting through the fact that I've got energetic granular collisions? And as a third point, I'm also interested in, can I actually use this pre-melting as a convenient way of using or introducing wetting into a granular flow to study very low volume fractions of moisture in a granular flow and those effects? That could be kind of a neat way of doing that. So I've got, this is my preliminary program of tests. I did 4 at -4, -2, -1, and 0 in the cold room just over there somewhere, not too far away. I used a rotation rate of 16 RPM. This was fast enough to give me a continuous flow, but slow enough not to have it too fast. Fill fraction of around about 1/2 to obviously optimize the length of the flow I was observing. And all of my data is just through high-speed imaging. And what I see is something like this. So it looks like pretty much like a classical granular flow. So I've got my quasi-solid region there that's following the trajectory of the drum, and I've got avalanching particles on the top there that are bouncing. Some of them are bouncing down the top. Okay. And the way I took the data was, obviously I haven't got a supercomputer, so I couldn't just spend 40 minutes recording all of this. Just way too much data. So instead, every 2 minutes, I took a half-second burst of high-speed images. Okay. And what I then did was I time averaged those bursts. So this is what I see when I've time averaged that clip that we've just seen. I can do a change point technique to locate the top surface there, so the shape of the interface. I've identified the point at which the granular flow drops off the drum up at the top there, and it meets the drum radius here. Okay, and if I interpolate those points, that gives me a mean surface inclination. But what I'm really interested in is the shear layer. So I want a nice reproducible way of identifying the shear or the velocities within that. So the blue line here is just the perpendicular to the green line, the average inclination from the drum center. And it's the profiles along there that I'll be looking at for the analysis. And also over each of those half-second imaging bursts, I've done a PIV analysis, and this shows you why it's been convenient, or why it's quite convenient to use those half-second bursts, because obviously we've got quite a noisy, energetic flow, and if I average out, then I get a relatively smooth set of data. So what we're seeing here, does this work? No. The black line there is the interface I found from the change point technique, and the color map in the background is vorticity. So blue here indicates clockwise vorticity, and red indicates counterclockwise vorticity. So we already see a difference in regime between the sort of tumbling basal layer, which is a dense granular flow, and the saltating particles on top, which are interacting with the air and have counterclockwise vorticity. But if I look at those profile lines that I showed you, those blue radial lines, and I can look at the development of the shear layer over time. it's a bit tricky like this because you can't quite see the difference, but the arrows actually get larger, indicating increasing velocities with time, and also the way in which it links in with the main returning drum flow also changes. So the main way I've tackled analysing this was just using dimension analysis. So the key properties of the experiment, or if I'm describing the shear velocity, the key experimental parameters are omega, the drum rotation rate, dp, the particle diameter, phi d, which is the number of particles essentially, tau is the time the experiment's lasted for, and then hs is I've measured is the shear layer thickness, and g sine alpha is the gravitational component in the direction of the shear flow. But the key parameter here is E, and that's the energy, or it's an energy density required for melting. Okay, so that has two components. One is the latent heat for melting, little l, and the other one is the specific heat capacity of the ice times the under temperature from freezing. So obviously the colder my cold room, the further below freezing, the higher the energy barrier to any kind of melting. Okay, so if you like, this is the key parameter in these experiments. So I've non-dimensionalized. I've got eight variables in 2 dimensions, and what I see is really that I've got 2 velocity scales. One is this dp omega, which is my experimentally set rotation, set by the rotation rate and the drum particle size, the particle size. And the second is this wave speed, hsg sine alpha, the square root of. Okay, I'm not really sure which one to use. So the interesting point, I think, is really how to think about this E here. So what I'm really interested in is understanding what the change to the shear layer velocity is as a function of melting, or degree of melting. So I'm going to say that I think that melting should be increasing with time and decreasing with E, the energy barrier to it. So on my x-axis here, I'm plotting a combination of those 2 groups. It looks like tau dp squared omega cubed over E. And I'm going to pose this as being a non-dimensional degree of wetting, if you like, or a degree of melting. So as I go from left to right on the horizontal axis there, I expect my flow to be increasingly wet. Okay. And on the left-hand axis here, I'm looking at the ratio of those 2 velocity scales, and I can see that in these experiments there's no real change. So I don't really care which velocity scale I'm going to use for the moment. So I'll choose the dp omega, because that's the one I definitely know, because those are the experimental conditions I set. And when I do that, if I look at my non-dimensional shear layer velocity there, compared with this degree of melting, I can see that from the beginning of my experiments to the end of my experiments, I'm seeing an increase in shear layer velocity of around about 14%. And a reasonable data collapse, the RMS residual from the linear best fit there is 6.1%. So I'm pretty confident with this. The only reason I've taken a linear fit is purely for convenience. I'm not sure what shape that should have. Obviously there would be some modelling effort before I'll be able to make a prediction about that. So would I be able to scale up to those large-scale ice avalanches I introduced before? Well, the types of Froude number you find in the field for medium or small to medium scale glacier collapses would be between 1 and 5. In my experiments, I'm seeing Froude numbers of around 1.4 to 1.6. So it's in the ballpark, but it's not over the whole range yet. So what happens as I go towards even higher degrees of moisture? So in those experiments, there was extremely low levels of moisture, sort of hundredths of a percent, but we're still seeing changes. There have been experiments in drum with hydrocarbon oil, and these show a transition towards surging regimes and ultimately a plug flow. And we see something similar. So this is letting my experiment keep going. I start to see these little snouty surges occurring. Okay, and these are really interesting because can you see the sort of snout formation at the front there? I'm starting to see slightly different structures. The second thing I see that's different is that the mechanism by which particles are mobilized outside the flow is different. So before, where I had the almost dry flow, particles were getting entrained through a basal shear mechanism, whereas here they're getting pushed along in front of them in a ploughing type mode. Also at the bottom, there's a very, very sharp interface between my little snouty flow and the sort of quasi-solid material beneath. Okay, so to go on with this, lots more tests over a wide range of temperatures. The crucial one obviously will be to go to very, very cold temperatures, which would be my control experiment of entirely dry ice, essentially. Also using different drum and particle geometries and non-melting and melting mixtures. So, as a conclusion, we've got an experiment, if you like, and a methodology in terms of the analysis, which is producing quite clean data. We've got a way of characterizing those shear flow velocities, and we've got a dimension analysis parameter space, which should give us some ideas for further study of these sort of melting flows. Okay, thank you very much.
Thank you, Barbara. Any questions? Yes, Nicholas.
So obviously you said when the temperature is high enough it melts, but even for cold or low temperatures, isn't there some kind of damage, at least on the surface, during the flow?
Yeah, so I checked, I did an image analysis of the particles before and after the experiment to see how much wear and tear there'd been on them. And it was fractions of a percent in terms of the mean particle diameters.
It doesn't change the velocity or whatever profiles?
Well, it's true that if there was significant sort of bits falling off the particles and smoothing and, I can't think of the word, abrasion. If there was significant abrasion, then yes, that would change the flow. But I wasn't observing that, so I tried to account for that.
Another factor that may be important is the reduction in melting point upon increase in pressure by the Closhes-Clapeyron equation.
Mm-hmm.
Because because the density decreases when something happens.
Something happens.
It changes. I mean, the reason you're able to skate is because it melts when you increase the pressure locally by the Closhes-Clapeyron equation. So that's another dimension.
Yeah.
Plus parameter that can be entered.
I think that's an urban myth that's actually the effective. People who are to skating and skiing don't think that's actually the effect. It's this other pre-wetting other things.
There's a lot of different factors that give you pre-melting. So like the surface curvature, for example, and the gas, or the humidity of the gas, or just the nature of the gas.
Yeah, but I mean, one way to test the effect of wetting is, I don't know how feasible it is, but we do it with carbon dioxide.
Yeah, exactly. Yeah.
Are there any other questions? I had a question. I don't think in your parameters you didn't say anything about the width of the drum. So I think that obviously will have a big effect on that.
Yeah, I agree. Yeah. So like I said, I'm not too worried about the drum as a configuration. It's just a convenient way of getting a shear flow. But yeah, you're right, it would certainly be.
All right, well, let's thank this morning's speakers once again.